Right now, we'd like to introduce our second guest speaker. We are fortunate enough to have two guest speakers. Rajender Chima is coming to us. He's a technical fellow, corporate senior vice president at SocioNext Solution SoC company. Rajender Chima has assumed various leadership roles in the semiconductor industry for the past 30 years in engineering and engineering management positions in establishing organizations. He has also been a founder and co-founder at startup companies. Deep understanding of advanced technologies, Rajender's primary focus is to solve issues, provide optimized hardware, software, and system solutions to end customers. Rajender currently heads the marketing and engineering departments at SocioNext America and supports the co-leading solutions team at SocioNext corporate office. Please welcome Rajender Chima to the stage.
Hey, thanks, Phil, for the introduction. Kind of overall agenda, high level is automotive market, ADAS and EV vehicle, what we see from industry and what's happening at a very high level. I think certainly we can have a lot more discussion follow up. Silicon deployment that's happening in automotive, certainly from a software to systems, and the automotive architecture evaluation kind of changing from where the market is converging, new requirement coming from ADAS, from a compute, from infotainment, and how these things are merging, and then certainly connectivity too. And then kind of little bit of my current job as the marketing guy at the company, kind of do some introduction of the SocioNext and what we do. And MCM and Chiplets will be a little bit kind of at high level again, what we as a company do and what we are offering. And then certainly a closing remark for what we as an industry need for the automotive. With that, if you look at today for autonomy and electric vehicle, you see all the different countries and states because of the environment requirements and global warming. Everybody wants to move the electric. Different countries, different states have a different requirement. For example, California, by 2035, we won't be selling the other cars. It's all going to be electric only. So key technology that's driving for enabling electric vehicles is the battery management, charging infrastructure, and certainly the key motors and the tractions. From autonomous, for ADAS and autonomous driving, enabling technologies, all the different types of sensors, LiDAR, radar, the camera sensors, and then high performance and heterogeneous computing. That's for all the AI. We need the different types of compute. And certainly to enable all of those things, you need a software and all the AI, from certainly AI execution and also the modeling. How do you optimize the models? And then certainly digital maps. If you look at this, the market, there's a different thoughts. This is the latest data from ABI research. There is the shift in terms of when the companies are really going to be, from an ADAS perspective, when it's going to start to happen. Different companies, different data from a different analyst shows differently, but certainly it is happening. Now, L5 certainly is a little complicated, and as was explained earlier, there's a different level. L2, L2 plus, L3 is happening right now. And certainly if you look at the robotaxis, certainly there are challenges. What you see in California, they're already happening right now. With that, if you look at the semiconductor in the automotive, where is the silicon being deployed and developed? There are many different sections in the car. If you look at this as the car model, you have the silicon for connectivity, for navigation, for vehicle-to-vehicle communication, for ADAS, which is stability control and anti-lock braking and all those things. And then you certainly have body electronics, where you control the windows and seats and all those things. Then safety system for blind spot detection based on the camera and other things. And then the other key that has been is the infotainment. All the new requirements coming in from the infotainment and how do you optimize and differentiate across the different OEMs. And then certainly the powertrain and the sensor suite. If you look at the current cars today, average car is packed with thousands of semiconductor components that controls everything from airbag to the engine. There are different parts of the automotive infotainment, as we talked earlier, audio, video, navigation, and display. If you look at the electric and personal comfort, you have a seat setting, the lighting, and the ACs and all those things. And if you look at from a safety, airbag, collision avoidance, and brake and park assist. And if you look at from a sensor and ADAS, you have a camera, LiDAR, radar, and also the compute and AI. And powertrain is engine and a fuel and transaction control. So all of these things in the car, if you look at it, And if there's so many different electronics components that goes in there, so many different components from a semiconductor that goes in there. We did some of the analysis earlier. If you look at the given car today, we talked about the different bandwidth requirement. If you look at just measure with the ADAS, the amount of cables required, you'd be surprised to hear it getting up to, see, just the weight of those cables is getting up to 20 to 30 kg. And every kg on the electronics car, on the electrical vehicle, it actually limits your distance. So everything is becoming important, and electronics is the key to drive it. All right. Now, if you look at the automotive architecture, certainly evaluations happen. It's getting to the next level. Different OEMs have a different architectures. All these companies drive their own platform architecture. Today, there are everybody's moving from kind of distributed to either the domain architecture or the zonal architecture. Certainly, moving to the zonal architecture to optimize the hardware. Now, what is it happening? Why is it happening? Right? The requirement is, if you look at from a domain or a zonal architecture from the sensor side, sensing, you have LiDAR, camera SoCs, radar SoCs, and sonar SoCs. This is the one that gets all the sensing data. And sensor hub is created, and from there you generate the data that goes to the main compute or can be localized computing. Then you have a cockpit where you have a smart display, where the infotainment and other things sits in, and also includes in-vehicle connectivity SoCs are there. And then you look at from the automotive computing perspective, you have the surround view SoCs, you have a zonal computing, front sensing SoC, high performance computing, and certainly a switches that connects all of them. That can be Ethernet or PCIe. I mean, the goal of all of this thing is to optimize the hardware and also to kind of enable all through the software. And if you look at it today, you're targeting kind of a different levels with autonomous driving. The requirement from a compute is coming from, for example, tens of thousands to hundreds of thousands of the requirement for DIMPS and TOPS. So these are all that's driving to new optimized silicon. Now, I think there was a talk earlier. Initial, if you look at the legacy days, OEMs used to work with the tier one used to work with the end suppliers to define the solutions and to build the chips. Today, a lot of OEMs are either already building their own silicon or looking at building their own silicon in the future. And some of them has already been announced. Some of them are open. I think earlier I was told, I think Robert told that we have about 10 plus OEMs building their own silicon, and a lot more are looking at how to build their own silicon going forward. So with that, semiconductor is becoming a key component, and with the software-defined automotives, they all want to build a platform, and from the platform drive the hardware that enables them for the future generation products. So with this, if you look at kind of from a market convergence perspective and integration perspective, right? Today, you have consumer chips, which is driven by the consumer process, targeting power optimization, security, and a low level of system failures. And then you have optimized silicon technology that defines the consumer product. Some of them were defined are being used for the automotive, but primarily designed for the consumer product. Like then the automotive, because of the ADAS, have a different requirements, development process. Certainly being functional safety is a big level, kind of which levels of ASIL do you support? That's driving kind of ASIL level security, ASIL level safety, and plus the security. And certainly the power and performance is also becoming important. That's driving to how do I optimize my SoC for power and performance leading up to the new technology nodes and which one to do. Earlier, if you look at traditionally from a foundry perspective, these were the big Apple companies, and those guys were driving the foundry, the leading node. Now, it's actually automotives are also getting right there. So they are designed that is starting today in the leading nodes especially for autonomous driving. And all of these combines together. And if you look at the further in the automotive, right, you have an automotive workload optimized AI models. This is being modeled and optimized in the data center, but loaded on the car. So this requires inferencing within the car. So those models are loaded in the car, have a different requirement to support the different ASIL levels, and then the different different autonomous level. So that's also driving. And all these things kind of lead up to building a new optimized, performance optimized SoCs for automotive. And we are seeing, and I think Cadence talked about this, they are in the middle of supporting all the customers from the IP and the tool perspective, and we, from a solution perspective, providing a silicon for that, building a custom silicon. We're also in the middle of those. Now, I think the multiple architectures are being optimized together to reduce the BOM cost. We're also seeing that common compute and AI, looking at the compute that can support both AI and infotainment, for example, to build a common compute that can use across those to, again, optimize the BOM cost, optimize the power. And we're also seeing today, I think you have probably seen it too, or will hear it. A lot of the automotive guys or the OEM guys are looking at when I enable the autonomous driving. Every hardware update, for example, you get the car that only supports level 2, and you want to go to support the level 3. The update on the hardware is very complicated and cumbersome. And that includes a lot of labor, and they also do their own planning. Instead, a lot of vendors are looking how to build everything from a hardware perspective, put in the car and enable through the software. And that's, again, enabling optimized hardware going forward. And certainly software-defined vehicle with the for support for optimizing new feature and enablement through over the air and multiple different ways to update the model. So if you look at this, right, so this is kind of from a technology perspective, automotive and consumer converging to define a new product here. And here is a typical, for example, on the different types of compute, you have a ADAS system with a multiple different sensors connected here, and the LiDAR, radar, and certainly the storage for multiple different things. And this is the infotainment, and they are all connected together through using the common compute through either PCI or Ethernet. Now, if you look at kind of further dig a little bit deeper, I'm still staying at the 1,000 feet level. If you look at the ADAS compute architecture today, you have kind of different types of sensors. You have a LiDAR, radar in here, different camera sensors on the different sites, and the typical, I mean, there are cars for different level support, maybe cameras from 4 to actually 40 cameras on the car to support different autonomous level. So in this car, you have different sensors which are aggregated together with a sensor hub. The data is brought to the main ADAS compute main SoC, where you have an AI accelerator and the different CPU for the compute and the AI for the inferencing. Now, this is, if you look at further dig deeper into this, the SoCs or the chips that are being built, what are inside this? You have safety island. Certainly, I mean, automotive has to have a safety island with the security and other things, which can be different computes here. Now you have a CPU system where you need a higher compute and different, depending upon the computer requirement, you can pick different versions of the ARM CPU or RISC-V or different CPUs available. And then certainly there's a GPU also for compute perspective for the graphics to support the other model. And then there are AI. As was talked earlier, a lot of the OEM guys are building their own AI accelerator or their own AI algorithm, which is poured into the hardware. So even though there is an AI chips available outside, they want to build their own, which is optimized for their own workloads and workflows, which they think is much more optimal and can be kind of enhanced in the future based on their learning. And then certainly the standard ones, multimedia systems and peripheral systems and all the other peripherals connected, all of these through some sort of a NOC. Now, other way to look at it is what's happening in the ADAS is like a data center in the car, except you need a functional safety. And the different components connected to the data center in the car is, on the peripheral side, is the different sensors from radar, LiDAR, to all those things. And this is also driving, earlier used to be, if you look at it, which technology node do I do? And moving to the smaller technology node, 3 nanometer, 5 nanometer, 4 nanometer is not cheaper. But the compute and the power requirement is driving to. So automotive is taking a lead to kind of looking into the leading node. And kind of, instead of driven by the mobile platform, the automotive guys along the data center is also getting their kind of requirements emerging toward the leading nodes. Certainly on the main SoC or the main compute and AI inferencing side. Now on the sensor side, it can be, the older technologies can be leveraged because the performance requirements are different. Now, if I go further in terms of, again, a very high level different infotainment system, you have a CPU, you have a GPU, you have a DSP in there, kind of different technology nodes required there. Now, you have a kind of in terms of CNN requirement, is 20 tops, maybe a different number from a different vendors. Output display connected to this, multiple different camera connected with the different types of interfaces. And this kind of, I mean, looking into how do we converge and kind of use the common architecture to support ADAS. A lot of things are happening. New architectures are evolving on this one. This is kind of a typical system that we see for the infotainment that we see today. Certainly is getting updated to kind of leverage the silicon across different platforms or different functions. That is from the infotainment perspective. Now, on the connectivity side, I think certainly connectivity to the external world to update the models. Also, from an ADAS perspective, typical concept is everything, the compute is integrated in the car. You get the models updated at the data center, optimized at the data center, and loaded into the weights and all the models updated into the car based on all the training done, offline training done in the data center. Now, there are different types of connecting. You can have a SIM-based where traditional like phone is working, but there's also a new way of connecting through V2X, which is vehicle to vehicle. And for the ADAS, so vehicle to vehicle connection or vehicle to stationary objects connected outside. So instead of having a compute in the car, I can have a compute sitting out on the road, on the streets. So I can have the ADAS enabled through the compute there, but through some sort of a communication connected to the car, where car can drive based on the compute done outside. That optimizes in terms of how much hardware do I need. There's pros and cons, and certainly for the dense area network or dense location, certainly makes sense in terms of optimizing hardware. And certainly the other thing that's happening with the V2X is you can get the information from the cars coming from the other direction in terms of a road condition, in terms of a traffic, in terms of a safety. So this is also happening today. And there's multiple different ways to connect the car in terms of for connectivity, for infotainment, connectivity for ADAS, connectivity for the software update. Now, kind of at a high level that we talked on the other side and from an industry perspective. Now, what is Socionics? What we do? We're founded in 2015. It's actually, even though we are about 8 years old company, but we have been doing silicon for last 40 plus years. It's a spin-off from Fujitsu and Panasonic. With a sales office worldwide and development office also worldwide. But it's not a traditional ASIC company. We are focused on custom solutions, SoC, where it's hardware, software, overall completely optimized based on the customer requirement. We have a strong background. This is a company, the people came to this company from a Fujitsu and Panasonic focused on the imaging side. That's the key technology required for the ADAS. And also from the compute, these are this part of the team that came to Socionics was also part of the Fujitsu supercomputers. So compute and imaging connected along with all the RF technologies that we have that enables us to support the automotive market. And for the automotive, we have been in production for last 15 plus years. This is the mass production with the standard products. But currently, a lot of SoCs or custom solutions are being built. And currently, we are doing the custom chips and custom solutions for based on the end customer requirement. For LiDAR, radar, and also the main SoC. And this is where it's a custom solution. We work with the customer to optimize hardware and software. We provide the complete solution. Now, that's the one model, doesn't necessarily have to be all the same model, but it can be either kind of traditional ASIC or most of the designs that we see is customer gives us a spec and we build everything together. We give them the device drivers and everything connected together with the BSP, and customer focuses on their application specific software. From an AI, for example, which models to load and how to optimize the software part of it. We do have some of the standard products too, mostly on the infotainment in terms of connectivity. Leading foundry experience, we are doing a designs for automotive in 5 and actually even 3 nanometer. And there is a discussion going on at 2 nanometer. If you look at a fabs are not going to be doing the automotive in next 2-3 years for 3 nanometer, for example. But we are working with the fab and the leading customer to enable the leading node-based designs, going even up to 2 nanometer. And we are also doing, for automotive, going up to 2 nanometer, but we're also doing a chiplets in 2 nanometer. For the compute, mostly from the infrastructure side, but those compute chips can also be leveraged for the automotive. There is a plan and roadmap to upgrade those to the functional safety, so it can also be used for the automotive. I'll briefly touch what that is. And we have a global development team across Europe, Japan, US, and India, with the sales office also worldwide. Now, our solution offering, if you look at it, traditional ASIC is this, where customer gives the netlist or RTL, and the vendor does all the design and give them finished tested parts. We are doing solutions where customer gives us a spec, and we do whole development, collaborating with the customer, of course, in terms of ensuring that we are meeting their requirement. And the customer focuses primarily on the software or the system side, which sits above the hardware. They optimize there. And if you look at the current today's right ASSPs, which are developed by the customer, is where vendor develops all the requirement based on the customer input, and that's a standard product, and that is sold to the other ones. This is kind of ASSP, but it's not an ASP. It's developed, designed for the specific customer based on their requirement, and this is customized for the customer only. It's not that we are reselling, it's optimized for each customer. The difference in these are you do develop with the specific customer and then you sell it to other ones too. So you dilute the values. This is, customer can have a proprietary value, they can leverage themselves. Now to do this, I think it certainly gets complicated when customer gives me a spec, high level spec, and hey, this is what I need to build. What do I take from a spec to fully tested parts giving back to them? So you need the architecture support. So we do software, hardware, co-optimization and build the architecture, microarchitecture. We do the design, which is front end and the physical design and all those things. And then when we do the design, we also have to make sure the functional safety requirement, full set requirements are met. We define the requirements, we work with the customer to look at the HSR, whole system level requirement, hardware safety requirements are HORs that implemented in the silicons. That's also ported to the silicon. And then certainly when the design is done, we go through the verification process, which is key in including all the error insertion, the safety verification. In the verification, we also use the emulation. For example, we work with the Cadence for the Palladium and Protium, where we use the Palladium platform to help with the verification. And we also have FPGA-based verification. Thirdly, we do a software development too, or a device driver development, for which we actually use the virtual models. We can run on either on the FPGA or actually on the software. So I have a model that I can run on the PC for the software development. We support that too. And then certainly from an implementation perspective, we go through the physical design, implement the design, ensuring that I'm meeting a thermal requirements, I'm meeting SIPI requirements, I'm meeting a performance, and all those things are implemented here. And then thirdly, in the end, we are responsible for manufacturing, where we manufacture the parts along with the package, work with the OSAT vendors to do the assembly test, and finally deliver the part that meets the customer requirement. And certainly here is the different things that we have to do from automotive specific requirement. For example, in terms of meeting a DPPM requirement, what do we do from the foundry, from the design, and in the manufacturing process to meet those, and all the different safety requirements driven by the standard. So we go through all of those. And certainly we can have a board discussion. I have a limited time, so I want to keep it at a very high level. We can certainly follow up if you have any question on me. Now, in terms of MCM and chiplets, we as a company has been doing this for some time. If you look at this MCM, for the current customers in the automotive domains, we are doing an MCM today, where you have the main SoC, the memory components are integrated in the one package in the MCM. I mean, certainly from a consumer or data center perspective, the challenges are different. When you go to automotive, from a reliability perspective, sitting in the car with a different thermal, that's a real different challenge. So certainly having support from a company like a Cadence, from all the tools, was certainly very, very helpful, very important in there. And the need for chiplet was already defined earlier. Need for chiplet is I have a chiplet, for example, here. I have a CPU chiplet, which is a compute. I have an IO chiplet, IO hub. And there I can integrate either the CPU for infrastructure, or I can have an AI accelerator added, multiple AI accelerator added, or if I need something else can be added. So there is a requirement is the need for chiplet. What is driving a chiplet market today compared to before? Because the silicon cost in the lower nodes is becoming very expensive. How do I do reticle size limit? First of all is my size. I cannot fit all the logic in the one. How do I fit? So I have to split the dies into multiple dies. Then the yield issue. When I get, especially getting 3 nanometer, 2 nanometer, the yield impact, the cost of the die is very expensive. How do I get the better yield? You split the dies into, so minimize the die, so the failure rate goes lower. And then also the faster it upgrades the product. You have a compute chiplet, you have an AI chiplet. In the future, I find I need to get the next generation product. I can leverage the same chiplet that I used before or somebody else's chiplet to get a quicker solution. Ability to upgrade with the latest chiplet. And we as a SocialNext, I think we did the press release earlier. We are working with the ARM and TSMC in developing multi-core ARM chiplet in 2 nanometer. This is going to be supporting for the hyperscale customers, infrastructure customers on the 5G side and on the edge SoC. And the same chiplet will be upgraded later to support the automotive also. And in general in the industry, automotive, MCM for the automotive is a little more challenging compared to the other one. But we are seeing today, a lot of customers are either already doing or want to move or will be moving towards doing the MCM to from a real estate perspective, from power perspective, and all those things. For example, the IOs, if the IOs are far, your SerDes power is how do I reduce the power? Pull everything closer. I think I already covered on this one. Now, at the end of the day, automotive development is very, very complex. And Robert explained pretty well all the complexities that you're going to see, what the challenges are going to be there. Now, to meet those, we need the support from EDA, from an EDA tool perspective, from the IPs. And Cadence is a good partner there helping us in terms of enable this, address these challenges. And we have been working closely for them to meet our current customer requirements and also looking at what's the future challenges are going to come and requirements are coming. How do we make sure we are aligned and we are developing those things to address those challenges? I mean, we as a company is focused on building a custom solution-based SoCs for ADAS or automotive. In that, we have a main SoC for the ADAS or autonomous driving. We are working with a multiple customer for LiDAR, radar, and also the sensor hub and the infotainment. And as I said earlier, we also have some of the standard products for the automotive, for example, IVI SoC to all the infotainment connectivity and email and all those types of things. At the end, thanks to Cadence, last but not least, thanks to the event organizing team, kind of helping organize this so we can discuss all as part of this industry. How do we make it better going forward? How do we work together better? How do we leverage knowledge base and also the availability from different parts in the industry to build a better solution for the end customer? You may be part of the OEM, you may be part of the tier one, you may be part of the development. How do we work together? So thanks for the team for organizing this. Thank you.
Thank you so much. That's a great presentation.